Thank you all for coming out. I realize that 9 a.m. on the Friday morning after the big party is not the most attractive time to be up and awake and moving around. Hopefully you at least have some coffee or something and maybe catching up a little bit. Those of you in the back, feel free to move up. I know it's a fairly small crowd, so feel free, we can kind of get to know each other a little bit better. My name's Evan. I'm an engineer at Stripe. I work on infrastructure and security there. I've been at Stripe for about 3.5 years, working there since early 2012. And today I'm going to talk sort of about how we think about PCI at Stripe and about how we deal with some of the challenges that come from PCI without impacting our ability to kind of keep moving forward and keep rapidly innovating on the product that we're building. So for those of you who are not familiar with Stripe or haven't run into us before, Stripe, or didn't hear Jorge's excellent spiel at Andy's keynote on Wednesday, Stripe is an online payments provider. If you're building an online mobile application or a business on the web, and you want your users to be able to pay you, Stripe is the easiest way to make that happen. We provide an API that hundreds of thousands of businesses around the world use in order to actually get paid for whatever it is that they're building. And Stripe is primarily focused on credit card payments and debit card payments. That's sort of been our traditional bread and butter, but we're also working with bank transfers and Bitcoin and other new and exciting and innovative or questionably political payment methods. If you haven't run into us before, we're working with everybody from the smallest new startups that you haven't heard of to some of the biggest names in tech right now, like Kickstarter or Lyft or Instacart, to some very, very big and well-known established businesses like the TED conference, Shopify, The Guardian, or the NFL. So we're kind of sort of playing the field, so to speak, in terms of the types of businesses that we're working with. But obviously with credit card payments being sort of the core of the product that we offer, PCI is a big part of what we have to think about. Now, Stripe has been PCI compliant since 2011. That was like right around the time that we launched. This is our very first certificate of compliance. It's obviously very important to us. We have to think about it a lot. We've been certified as a level 1 service provider, and for those of you who have not suffered through PCI compliance in the same way that I have, that is the most stringent level of audit that is available, that is available as part of the PCI process. And in 2012, we moved all of our infrastructure into AWS, including our PCI infrastructure. And we've been in AWS entirely ever since then, running both our PCI and our non-PCI infrastructure in AWS. So PCI is not a simple standard. I went and looked it up. It's 115 pages total, and that's just the core spec itself. If you look throughout the documentation that's published by the PCI Council, there are hundreds of additional pages of implementation details and supplemental information and Talmudic interpretation, covering the various aspects and details of how to implement PCI within your organization. And we were told when we were getting started that PCI was going to be this big nightmare. It was going to weigh us down. It was going to prevent us from being able to move quickly. It was going to make us stodgy and old and slow moving before we were even old. And so the way that we approached this problem is we kind of sat down with sort of a blank slate, and we thought, well, what really matters here? What really matters, like from a security perspective, from sort of building the most secure system that we can? Because that's what really PCI is all about, is trying to make sure that your users' sensitive information is secure. And what we found is that by taking this approach, we could often come up with systems that were more secure than the PCI experts recommended, and yet at the same time were easier for us to maintain and less of a burden. And so today we'll talk about a few examples of that. I'm going to go through 3 different cases where we were able to start from sort of a clean slate and find ways to make things better in ways that might have contradicted what sort of the standard best practices are. And the strategy is very useful for PCI. We found it to be very, very helpful for us to sort of accomplish PCI's goals and satisfy our compliance requirements, and also continue to innovate rapidly. But it's not just limited to PCI. This is something that's useful sort of anywhere in your organization. It's useful for establishing infrastructure, for thinking about product. In some sense, Stripe itself is founded on the principle, on this idea that that we want to challenge the assumptions that payments has to be hard. And so that's something that idea is something that's very core to us as an organization. So I'm going to go through 3 different stories today, all of which are actual, real things that have happened at Stripe, that we've implemented, that we're running in production today. And so I'm going to talk first about sort of a very broad problem, which is just how we approach PCI in general. And some early decisions that we made that ended up helping us out a lot in terms of managing the complexity of PCI. And then second, I'm going to look at a very, very specific PCI requirement that often can create a lot of maintenance burden and operational burden, and show how we were able to largely eliminate it from the day-to-day operations at Stripe. And then finally, just to show how this can be used outside of the scope of PCI, I'm going to talk about an infrastructure problem that we ran into that's something sort of fairly near and dear to my heart. An infrastructure problem that we ran into where using the same techniques we were able to solve a problem completely outside of the PCI and security space. So the first example that I want to walk through is very fundamental to how we approach PCI at Stripe. And it shows that when you re-examine your problems from the ground up, when you look at it from first principles, you can often change the constraints of your problems in a way that you might not have imagined. Now, if you had to imagine what the Stripe API looked like without really knowing too much about the details of what we do, you'd probably imagine that it looks something like this. Credit card numbers come in, credit card numbers go out. But in practice, the Stripe API is actually significantly more complicated. Not only are we doing much more than simply taking credit card numbers and passing them out to the credit card networks, but we're also, for starters, taking in other pieces of information, things like API keys or occasionally customer personal information. Not to mention a bunch of information that just isn't actually as sensitive at all, really, like IP addresses, which are somewhat sensitive, but certainly not to the same degree that credit card numbers are. And internally, once we get that information, we do a lot more than simply pass it on to the credit card networks. We have to deal with problems like authenticating incoming API requests, making sure that they're actually allowed to make those requests. We have to do things like currency exchange for our users. We allow our users to charge in one currency, get paid out in another currency. We send out notifications to our users when events happen on their account so they can keep track of it. We do fraud detection, which is obviously sort of very critical for an online payments business. And all of this incoming information is used in various parts of these different systems. Now, in a traditional application, you see some companies that build their systems like that. They just kind of throw everything together. If you're just starting on an application, if you're just getting started and hacking on it, you'd probably do this too. Just kind of like do the quickest thing, do all of it in one place. We'll sort it out later. And the big problem, specifically when you're dealing with PCI or other sort of compliance requirements, is that kind of draws this big red line around the entirety of your application and puts it all in scope for PCI, which means that for everything that you're doing, you have to satisfy PCI's requirements. Now, PCI has some very good requirements. PCI also has some somewhat more questionable requirements. Things like PCI tends to dictate the way in which you do development. And as a startup, that's something that we don't really like. We think that in general, we can get a lot of the benefits of the types of things that PCI likes without necessarily using the exact strategies that they dictate. And so we realized that if we were subject to this sort of giant bubble of PCI, it would be a huge burden on us in terms of being able to innovate quickly. But when we sat down and actually considered our options and thought about sort of just what the problem space was, what we realized is that it actually turns out that this data can be really fairly effectively compartmentalized. So for example, let's talk about fraud detection. I can't go too much into the details of how our fraud detection works, but I can say that one of the big inputs into our fraud detection algorithms has to do with how a credit card has been used in the past. As it turns out, if you use your card in the US almost consistently, and then all of a sudden a charge shows up from somewhere in Southeast Asia, something funny is probably going on. And this idea of identifying sort of sequential uses of a card is really important to our fraud algorithms. But in order to apply those types of algorithms, it turns out you don't actually need the credit card number. All you need some sort of unique identifier that stays the same from transaction to transaction, so that you can always tell not what the credit card number is, but that the same credit card comes up. And on top of that, for a lot of these other components, we maybe just don't even need the credit card numbers at all. Currency exchange is just, I mean, there's money moving around still, but it's just a question of like, what currency are we converting from, what currency are we converting to, and how much of it do we need? And these other things just don't even touch credit card numbers at all. So we sort of wiped the slate clean, we started over, we started thinking about the problem space a little bit more. And we asked ourselves sort of, who actually needs to see that credit card number? Who needs to have access to the actual credit card number itself? And the answer is that there is only one thing that needs access to the actual credit card number, and that is the actual credit card networks. And nobody else needs to see it. Nobody else needs to see the credit card number, ever. Everybody else just needs to see a unique identifier of some sort of stand-in for the credit card number that's always the same, so it's always the same representation, but not the actual card number itself. And from the perspective of PCI, from the perspective of compliance, this idea of a sort of stand-in for the credit card number, or a token in the parlance of PCI, is not considered to be PCI sensitive. And so applications which only handle tokens are not in PCI scope. So we built a component that just created tokens. This is all it does. Credit card numbers come in. It has no awareness of what the application is doing. All it knows is that looks like a credit card. It takes the credit card out. It replaces it with a unique identifier. It generates one if it has to, if there's not one there already. And then it passes it on to the rest of our infrastructure. And once it's done that, because it no longer contains a credit card number, because it only contains the token, it's no longer PCI sensitive. And that entire application that I showed you before, all the different fraud detection and authorization components, none of those are considered in scope for PCI. And so none of them are subject to the burdens of compliance. So, OK, so what happens when we actually decide that we want to charge a credit card number? It's pretty easy. All you do is you take that token, you hand it back to the tokenizer. Tokenizer turns into a detokenizer, which is basically the same thing, just running in reverse. It substitutes in the actual credit card number and sends it up to the card networks. And one thing that we've done with this application, which has been extraordinarily useful for us from a development perspective, is we tried to make the tokenizer as lightweight as possible, so that it actually has almost no awareness of what the underlying Stripe application is doing. All it knows is that there's a credit card number there, or I need to replace a credit card number right there. And by doing that, we're able to satisfy our PCI compliance requirements in this sort of fairly narrow component. Now, obviously, the tokenizer is in scope. The tokenizer does have to be PCI compliant. We do a bunch of stuff in order to make it secure. It is, in some sense, sort of the most sensitive component that we have, because not only is it handling credit card numbers, but in fact, all incoming API requests go first through this component, which means that it's handling, in fact, all sensitive information that passes through our systems. But it's a very simple component to maintain. It's a very simple component to develop. And it's much, much easier to manage. And so even though the requirements on that one component are maybe higher than they might have been on the entire system, it's much easier to satisfy those requirements. And as a result of that, I actually went and checked to see exactly how much easier it is. So if you look at our infrastructure today, only 1 out of every 30 instances that we run at Stripe is dedicated to PCI. The other 29 are completely out of PCI scope. Auditors don't even care that they exist. All we have to do is just show them that thin little sliver of PCI-sensitive infrastructure, and they're satisfied with our compliance status. Now, we've used this approach in more than just our own internal PCI infrastructure. If any of you have ever integrated with Stripe before or used Stripe, you'll know that we have a client library titled Stripe.js. It's a JavaScript library which effectively accomplishes the same thing for our users. They take credit card numbers and submit them to our servers instead of to their servers, and we give them back a token, which they can use as a placeholder for the actual credit card numbers. And in that way, they, in fact, don't have to go through any sort of audit process at all. They have to fill out an SAQA, which is the self-assessment questionnaire, which is the sort of the easiest of the self-assessment processes you can go through in PCI. But it's largely a formality, because since their systems aren't storing or transmitting credit card numbers, they're never in scope for PCI. And this strategy is definitely growing in popularity. You know, we were doing this a couple years ago, but a lot of people are doing this now. Take, for example, how many of you guys have iPhones? Does anybody here have an iPhone? Yeah, I see a couple hands. Have any of you guys paid with Apple Pay before? Yeah? So the way that Apple Pay works actually uses a very similar strategy, this idea of tokenization. When you add a card to your Apple Pay account, the thing that is stored on your phone and the thing that you use to pay with Apple Pay is not actually your credit card number. It's a unique identifier that's unique to your device that's provisioned just for your device and represents a stand-in that you can revoke and manage independently. But also, it means that you're not passing around the sensitive 16-digit actual underlying credit card number. So Apple Pay is doing this, has been doing this for it must be about a year at this point. Android Pay recently launched. They're planning to use a fairly similar strategy. So this idea of using tokenization as a stand-in for as a stand-in for dealing with sort of broadly scoped compliance and broadly scoped exposure is becoming more and more popular over time. So I think the important takeaway here is that understanding your boundaries and understanding your edge conditions is really important and really valuable. When you understand your boundaries, you can shrink them because you can find things that are outside of those boundaries. And once you've done that, maybe you'll find that you can avoid security considerations entirely. For example, those of our users who use Stripe JS are able to, by sort of defining their boundaries carefully, avoid PCI obligations entirely. And in cases where you can't do that, you can often make them somebody else's problem. So for example, using services like VPC from AWS or security groups, we're able to sort of not have to worry about things like firewalls at all because AWS provides those services for us. So the second story that I want to talk about, we just talked about sort of a broad infrastructure problem that we were able to sort of design around at a very high level in a very early stage of our infrastructure development. I now want to talk about a case where a very, very specific solution to a very specific problem that we ran into. And this has to do with PCI's requirement 6.6. Now, for those of you who are not familiar with PCI or have not spent as much time poring over the specs as I have, PCI requirement 6.6, PCI is grouped into 12 high-level requirements dealing with the various top-level aspects of what they feel are important security properties to have, and they break those down into sub-requirements and sub-sub-requirements and sub-sub-sub-sub-requirements, and it just kind of keeps on going. Requirement 6 in general deals with making sure that the applications that you are developing are secure. And requirement 6.6 states that you need to make sure that you are addressing known vulnerabilities, known classes of vulnerabilities in your application. Now, I mentioned before that there are sort of several hundred pages of documentation and supplemental information around PCI. Most of it is kind of like more high-level stuff or just like dealing with things in aggregate, talking about how you deal with mobile applications or talking about how you think about phone networks, for example. But a couple of the requirements have their own dedicated document. There are two of them. And requirement 6.6 is one of those requirements that has this sort of detailed supplement. It's a complex requirement to actually implement because this idea that you just want to deal with common vulnerabilities is much more, there's much more behind that than there is in just a simple statement. So this comes with a sort of 12-page supplemental document about what exactly they meant in that one-line throwaway sentence. But the typical approach for handling this requirement is fairly straightforward. You use something called a web application firewall, or a WAF, similar to the product that AWS just released earlier this week. I don't know if anybody's using it for PCI yet, but I'm sure it's only a matter of time. The web application firewalls are different from the firewalls that you may be used to. Usually firewalls work at the IP layer, at the layer 3 or layer 4, identifying suspicious packets. A web application firewall works at the application layer. It's a layer 7 firewall. It works by actually inspecting the incoming HTTP requests or whatever protocol it is that you're speaking, looking at it semantically for common classes of vulnerabilities. So the purpose of a web application firewall is to detect malicious traffic and either reject it or notify an administrator for further investigation. In practice, running a WAF is kind of terrible. I don't know if any of you have ever done it. It's not a lot of fun because it turns out that if you're using some pre-existing sort of sanctioned web application firewall package, it comes with this pre-existing set of rules that try to detect common classes of vulnerabilities. Like this looks like an XSS attack, or this looks like a SQL injection. But it's really hard to write a generic set of rules that understands common vulnerabilities without being incredibly broad. As an example, when Stripe was running a WAF internally, we used mod security for a period of time, which is a fairly popular open source WAF. It literally has a rule that will fire if your request contains the string space or space, because it's trying to find any SQL injection that might be anywhere in your request. And this kind of overly broad rule set results in sort of one of two things. If you're running your WAF in enforcing mode, it means that it rejects legitimate traffic, which you never want. Or if you're running it in alert mode, it means that some administrator has to pour through a bunch of requests that fall into exactly one of two buckets, totally innocuous or potentially company-ending serious. And if anybody's ever studied cognitive biases before, if anybody's ever looked into the cognitive biases about how humans process just like large volumes of information, this idea of like, this is fine, 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 oh, crap. This is not good. Humans are not good at that. They miss things, they just don't notice it. It's not a good approach. So again, we sort of started from a blank slate and started thinking about what's the actual goal here? What are we trying to do? And what we're trying to do is we're trying to protect against common classes of vulnerability, sort of well-known, well-documented, like broad classes of bugs. And it turns out that there's a very easy document that covers broad classes of common bugs. It comes from OWASP, the Open Web Application Security Project. Every couple of years, they publish a top 10 list of the 10 most common classes of vulnerabilities. So we went through and we looked at all of them. Here's an example page where they walk through how exploitable a particular bug is, how likely it is, how easy it is to tell when something's when it's being abused. And we found that for each of these 10 common vulnerabilities, there are standard programming tactics that just make them go away. If you talk about something like an XSS attack, cross-site scripting, there's a very standard tactic for dealing with that. All you have to do is make sure you're escaping user-provided text. I mean, that can be easier said than done, but the basic idea is pretty straightforward. And there are tools that do this, that construct your program so that they do this automatically and transparently. Now, Stripe is primarily a JSON-based HTTP API. We don't return HTML. So XSS isn't really a problem for us. Injection, on the other hand, definitely a problem for us. We definitely accept untrusted input, which is sort of the fundamental basis of injection. And we have a tendency to store it in our database because that's kind of what we do. So injection was a problem that we needed to be able to address in order to say that we were dealing with common classes of vulnerabilities. So what is a SQL injection anyway? Maybe this will be sort of fairly familiar to you guys, but I'll try to run through this quickly. And I'm going to work in Go because that's actually what our PCI application is written in these days. If all SQL injection vulnerabilities fundamentally have the same class of problem, you're taking untrusted user input and you're dropping it directly into an interpreted query language, such as SQL. And it's possible to do this safely. There are functions and routines that can escape that code to make sure that it's not using any special characters or anything like that. But that's kind of hard. And it's easy to get wrong. For any of you who've ever worked in PHP and had to go from MySQL escape string to MySQL real escape string, you might be familiar with this class of problem. So how can you solve this generally? Like, what can you do to be confident that you're not writing a SQL injection? Well, it probably looks something a little bit more like this. You use placeholders in the query, and then you let the database itself incorporate those values into the query that actually gets run. Because it turns out the databases know how SQL works because they kind of have to figure it out. So they're able to substitute that variable safely into the query. So how can we detect queries that are potentially unsafe? How can we detect this in an automated way such that we can be confident that our application isn't vulnerable to these classes of vulnerabilities? Well, it's fairly straightforward, as it turns out. All you need to do is find cases where any sort of string interpolation or string generation is happening and then being passed to the database. And as long as you're using compile time constant strings like this, you can be confident that those queries can't possibly be vulnerable to a SQL injection. If it's a compile time constant, there's no user-provided input that's part of the query, and an injection simply can't happen. So we wrote a tool to look for that. We wrote a tool called SafeSQL, which uses some really cool AST and parser functionality in the Go language to parse our code base, to look through the entire code base, look for anywhere that we're passing queries to a SQL database, and see if they're compile time constants. And if they are, then that's great. And if they aren't, then you flag it, because that could be a problem. It's not necessarily unsafe, but it's impossible for the computer to know with confidence that it is safe. And so we wrote this tool. We open sourced it. There's the URLs at the top of the slide. You guys can go fetch it. If you happen to be writing Go code that's interacting with SQL, you should totally check it out. It's a lot of fun. Very, very easy to use. But I think the point's a little bit broader than that. The idea here is that by using SafeSQL and by using tools like SafeSQL, we worked with our PCI auditors, or our QSAs in industry parlance, to demonstrate that not only were our applications not vulnerable to common vulnerabilities now, but that also it was impossible to add new vulnerabilities, because we had automated detection at the time that the code was written to find these vulnerabilities and flag them. We built this tool into our continuous integration system. It's impossible, given our deployment processes, to roll out code that has a SQL injection, because it would cause our CI to fail, and we just wouldn't roll out the code. And so the result is that we're no longer, with a WAF, the strategy that you take is that you're trying to detect exploitation as it happens. In some sense, you're addressing something after it's already become a problem. With tools like SafeSQL, and by sort of addressing the fundamental goal of protecting against common vulnerabilities, rather than detecting exploitation, we can prevent it from ever happening or ever being possible. And the result is that we no longer have to run a web application firewall. We no longer have to deal with that complexity or operational burden. And yet, our application is in some way more secure than it would have been had we not had we been using a WAF, because we know that these vulnerabilities simply aren't present. So like I said, if you're writing Go, I definitely encourage you to check this out. It's also probably, if you're writing Go and you want to evaluate for other types of vulnerabilities like this, it's a pretty good template. The code's very straightforward. I think it's about 300 lines of code or so. It's very easy to do with Go's internal parsers. A lot of languages have AST parsers, so if you're working in other languages, you can probably construct similar things as well. It's a really cool strategy and a really fun way to try and detect these kinds of problems. The last story I want to talk about is not actually related to PCI. Nor is it related to even security particularly. But this is a scenario where we use the same strategy of understanding the problem really well and working from first principles and sort of sitting down, starting from a blank slate and thinking about the problem. And we were able to come up with a much better solution than we had previously. And this solved for us a persistent performance problem. I'm sure that I'm not the first person to stand in front of you and say that we are moving towards a microservice architecture. Probably heard that before this week, once or twice at least, maybe. But we are. It's a fairly common story, especially for startups and about our stage of growth, where we're finding that our application is becoming a little bit more difficult to manage as it grows, and we want to use microservices as a strategy for defining clean boundaries. Speaking of defining clean boundaries, and just sort of carving up our application a little bit. One big problem with moving towards a microservice model is service discovery. If you have all of these different microservices and you want them to be able to talk to each other, well, they kind of need to be able to find each other first. And so when we sat down and started looking at service discovery as a problem, we decided to use an open source tool that was fairly recently released called Consul. For those of you who are familiar with Vagrant or Terraform or Vault or any of those groups of projects, this is out of the same company that does those, out of HashiCorp. Consul is a tool for service discovery, and it's from those same people. Service discovery is basically the core of what it does. It's pretty straightforward. You write a simple JSON file, you drop it into a directory, you define the services, you include things like port numbers and names of the services. You can even define checks if you want to. So if you want to say that this service is not considered healthy unless this command returns successfully, and the Consul API will automatically run that check and remove the host from the registry if that service fails its health check. So it's fairly flexible. It's sort of easy primitives to work with. Internally, this is a screenshot from their documentation. Consul uses a consensus protocol called Raft in order to keep track of state. For those of you who are not familiar with Raft, it's a fairly new protocol in the consensus space. It's the same class of protocol as Paxos or Zab from the Zookeeper project. The idea of having several different distributed servers agree on something is one of those fairly challenging problems in computer science. We have a couple different protocols that are known to deal with that problem in a way that's sort of correct and ensures that they will always come to a consistent answer if they come to an answer at all, which I'll get back to that one. But so Raft is a similar protocol to in those other classes. It's a fairly recent one. It's kind of popular right now. It's got a nice, easy implementation. And Consul uses Raft in order to synchronize state across a pool of servers. And then if you make a query, if you want to look up a service, try to find somebody to reach out to, what ends up happening is that all queries get forwarded to whoever is the current leader in the server cluster. And the leader returns the answer. So we tested Consul, and it looked pretty good. It's very easy to integrate with. It's very easy to use. We used it in a couple of sort of limited applications that were not super critical. That were not, big deal if they broke. And things were mostly OK. We didn't really see any major problems. And so once we were confident that we weren't seeing any major problems, we took every instance of service discovery that was happening within Stripe. Previously, it had been happening through things like configuration files and stuff like that, which is not fun. And we replaced all of our service discovery with console lookups. And so it was great for about a week, and then it was not great. And then it started looking about like this. That is the 90th percentile latency, the 90th percentile amount of time that we spent in a single API request doing console lookups. And as you can see, it started under normal conditions in the tens of milliseconds, which is fine. And then all of a sudden, it went to tens of seconds, which is not fine. Tens of seconds. Spending 50 seconds just doing service discovery is not really a good scenario for us. When we started looking into it, what we found is that under certain circumstances, the console server cluster would decide to elect a new leader. And then something would go wrong, and it would decide to elect another new leader. And it would get stuck in this cycle of continuous re-elections. And when that happens, if there's no consistent leader, there's no way to return queries from the leader. And so you end up with something like this. Now, we worked with the upstreams. We fixed some problems in our code. The reason that spiked to as high as it did was because we didn't have timeouts on our console lookups. So as a reminder, just keep this in mind when you're doing network calls. Set a timeout on them, or you're never going to like what happens instead. So we added timeouts. It made things better. We worked with upstream. They fixed bugs. It made things better. But we were still having persistent problems intermittently where console would get sort of stuck in this state, and we wouldn't be able to do any of our service discovery at all. So just like the other few times, we started from a blank slate, and we thought through the problem again. And we tried to figure out what it was that was really important about service discovery. And we decided that the real question is that what are the actual requirements for accessing this data? Some of you may be familiar with the CAP theorem. CAP theorem states that of consistency, availability, and partition tolerance, you get to pick at most two. Some people only manage to pick one. It's OK. I don't love the CAP theorem. The main problem that I have with the CAP theorem is that it suggests that you have the option of trading away partition tolerance, which if you're building a distributed system, that's kind of meaningless. So I tend to actually use a slightly different algorithm. I just wanted to set this up just so that you guys have some context. There's another way of thinking about this that's a little bit more useful to us, and it's called the Passelk principle. And it basically kind of separates the idea of partition states and non-partition states. When you're in a partition state, you get to choose between either having availability or consistency, because again, you don't get to trade away partition tolerance in a distributed system. And when you're not in a partition state, there are sort of two different options you can take. You can either optimize for low latency, or you can optimize for consistency. And latency in a non-partition state and availability in a partition state are often sort of fairly analogous. But let's think about sort of if we're using a Paxos or a Zookeeper-like consensus protocol, what are we choosing? Well, the answer is that we're choosing consistency. We are always choosing consistency. We are always choosing consistency over availability. We are always choosing consistency over latency. Now, let's talk instead, what do you want from service discovery? Is consistency something that you care about from service discovery? Do you care if it's maybe 30 seconds out of date on whether or not a node is online? And the answer is almost certainly no. When you're doing service discovery as a problem, stale data is almost always better than no data. And so you actually want a system that consistently makes the opposite choices of a Raft-based consensus protocol. So we sat down, and we thought about it, and we said, well, OK, we have the system that gives us these properties, and we want a system that gives us these properties, and how can we do that? So, well, we decided to add a layer of caching. For those of you who have not seen this quote before, there's a fairly famous quote from Phil Carlton. There are only two hard problems in computer science: cache invalidation and naming things. And service discovery is pretty much just looking up names, and so we decided to take both of them on at the same time. And so what we did is that we added a caching layer to console. Every 15 seconds, we take the entirety of the console database and we dump it out to a file. And then we would use that file and serve it in a non-distributed, non-consensus-driven way. If console was down, we wouldn't be able to dump that file. We might serve stale data. But we would at least be able to serve something, which is better than having our latency spike to 50 seconds on a single API request. And what do we decide to use for this? Well, it turns out that there's already sort of a fairly well-known distributed algorithm, distributed protocol for handling like name lookups, I guess it is, some sort of a name server, I guess. So we actually decided to use DNS for our service discovery, which is a feature the console already has. We kind of stole it, but their version is backed by the Raft consensus cluster, and ours was backed by a zone file that we spat out every 15 seconds. So we'd spit out this zone file, and we'd load it into our internal DNS servers, which we were already running, which we already know how to run, which have no coordination overhead or consensus protocols. And every piece of software in existence knows how to do DNS lookups. And so it's something that's sort of easy for us to integrate with. So we rolled out this change. We switched to using these DNS-based lookups out of this cache. And since then, we've had exactly one console incident in the last 6 months, and it related to a kernel bug. It was not fun. But other than that, it's been way better than the system that we had before, where we were sort of constantly experiencing the ways in which this sort of system, which didn't have the properties that we wanted, was impacting our availability. So whether you're thinking about ways to sort of narrow the scope of compliance or change the boundaries of your problem, whether you're using static analysis to satisfy individual requirements, working on the reliability of your core systems, or even just trying to rethink how payments work, starting from a blank slate and making sure that you understand the fundamental problem that it is you're trying to solve and making sure that you define that well often results in better solutions than you might have thought possible. The idea of questioning assumptions, of starting from first principles, of finding the best solution is something that's very core to Stripe's values. It's something that we value very, very highly. I think it's a big part of the company that we are today, and I think it's a very empowering idea because it enables you to come up with solutions to problems that other people might not have thought possible. So I'm supposed to remind you all to complete your evaluations, apparently. And thank you all for coming. If you guys have any questions, I'd be happy to answer those.